Okay, thank you very much, Professor Takashi Hiyama, sorry. And then next, I'm going to invite Mr. Dean Safari as our third plenary speaker. Okay, and then Mr. Dean Sharafi is heading system management, the operator of Southwest Interconnected System in Australia, and he has over 25 years of experience in power system engineering, which includes power system protections, high voltage systems, and then asset management and power system electricity market operations. And beside, he has published many papers on power system protections, conditions monitoring, and asset management and power system operations. And he also, as a lecturer at Curtin University, a seasonal academic on power system earthing. So ladies and gentlemen, let's give applause to Mr. Dean Sarafi. Time's yours.
Assalamu alaikum wa rahmatullahi wa barakatuh and good morning. I would like to thank the Universitat Dian Nuswantoro for inviting me here today. And I would like to start my presentation with this beautiful photo. So I don't know if you know that 2 minutes energy from the sun that reaches the earth is enough to power the whole humanity energy needs for 1 complete year. 2 minutes and 1 year, not only electricity, transportation, heating, cooling, everything. So there is a potential that we haven't even tapped into yet. So there is a lot more to go. Let me first start with Indonesian energy landscape. I'm sure you know all about it, all these statistics. Indonesia is a net energy exporter and a lot of potential to grow. So this is the objective of you here, to make sure that this full potential is realized. But this conference is about retrospect and prospect. So looking back, looking what is coming in the future. You can see that the household consumption of energy has increased year by year in Indonesia. You can see this is a very sustainable and sustained growth of energy usage for households. If you look at the makeup of this energy, you see from 2008, there is a lot of kerosene here in this graph. But then continuously this energy consumption mix have changed. You can see in 2011, for example, electricity and LPG is taking the place of kerosene. And in 2018, just last year, the whole energy consumption in household was for electricity and LPG. So this is a change. This is a change really that needs to be considered. And the peak load in megawatt has consistently been, the trend is upwards. So this is the background for Indonesia, and this information from the Ministry of Energy. Let me talk to you about how is Australia doing. The scenery in Australia is also changing, but in a different way. This is the mix-up of energy mix in Australia in 1998. You can see there is a lot of coal. This is similar to Indonesia. But then in 2008, you can see that in this mix, the coal has reduced, and then we have wind and solar, rooftop solar. And going forward, you can see that coal is going to reduce even further, and we have rooftop solar will have larger scale solar and a lot of wind. So what does it mean really for an industry that is going through this rapid rate of change? You can see what is happening behind the meter. In households, there are a lot of people who are changing the way energy system is working. If you look at the first one, there is a house without anything. So it is a load that is consuming electricity. In second one, the house has a solar on its roof. And in third one, the house has a solar and energy storage. The global mix of energy, this is from Bloomberg. You can see the coal is consistent until almost now, but there is a dip. You know, towards the end, you can see the rise and fall of nuclear energy. And you can, if you look at the top one, you can see there are shoots of new type of energy just coming into the mix. If you look forward, you can see that this will grow to be almost half of the energy mix of the future. So this is what we are going to prepare for. This is what the industry needs to prepare for. I show this because this shows the ratio of decentralization. Showed you that customers are putting rooftop solar on their PV, on their roofs. I have seen also in Semarang, there are some buildings with rooftop solar. But in Australia, 1 in 3 houses have rooftop solar. So you can see that the rate of decentralization of energy is going to be very, very rapid, and in some countries very, very different. So the challenges that we are going to deal with are going to be different. But you can see that Australia is almost on top of any other country in this regard. So I think there is a lot for Indonesia to learn from the mistakes and the pitfalls Australia has gone through. You know, leading edge is always the bleeding edge. But the benefit of those people who come later is the benefit of hindsight. They will learn whatever is there for them, and they will not do the same mistakes that others have done. So I think it is very good for Indonesia to take heed of this. This is a picture of city of Perth. Actually, I took this picture from my office, from the window of my office, which is on level 44 of a building in Perth. You can see a very sunny day here. When we have a sunny day like this, there is a lot of energy that is coming into the grid from people's houses, especially in this month. So you can see that these people who all have solar panel have an amount of energy that is 3 times as big as the largest generator in the grid, 3 times bigger. So this situation can change to this very quickly. You can see my shadow in the window. This is a photo I took again from the same scenery, but on a different day. So you can see for a system operator who wants to manage this energy, that has a lot of difficulty, because I know you can forecast this, but this situation can change in a matter of half an hour. And then the sun comes out. And then you end up with 1.2 gigawatt of energy that you didn't know how to account for. This is the map of Australia. And you can see a lot of red areas. So these red areas, in 5 years' time, will be net generators. Means they won't be consuming electricity, they will be producing electricity constantly, pumping it into the grid. You can see that both in Western Australia and east side of Australia, there are a lot of red areas. I'm going to talk to you about this part, which I'm living in, Western Australia, and the grid that I've highlighted here. If you look at this, this shows a duck curve. We call it duck because it looks like a duck, right? Because if you look at it, it has a belly that is growing every year. And where else can it grow to? Because at some point, the system will be unmanageable. So you can't manage a power system when there is a lot of generation only during certain hours of the day, and then you need to actually gain a lot of generation here. Towards the end of the day, you need to have a lot of generators ready to satisfy this. Otherwise, the power system will go black. And this story is not only for Australia. I can show you Californians' duck curve. So you can see they are facing the same problem. Indonesia doesn't have this problem, but Indonesia can learn from what others have done to manage the situation. Now, the weather is so important, not only on the load side, but only on the generation side. Previously, the planners only looked at the weather on the load. So if it was hot, you knew that the load was going to be up. It was very cold, you knew that the load was going to be very up. But now the weather is both on the generation and on the load side. So it makes it so difficult to plan for future power networks. This graph here shows the output of a single rooftop PV during the year. So you can see it can be up, it can be down. What I've highlighted here in the red is just the average, but it can be anywhere. So it will be very, very hard to manage this situation. You can see a lot of houses in Australia like this. Part of the roof is rooftop panel. This is my own inverter in my house. I have an application that tracks the output of the solar that I have on my roof. And if you can see here, I don't know if I can show you with a laser. On this side, it says Dean's home. That's my home. And you can see, even it's not 8 o'clock in the morning, and I'm pumping like 2.5 kilowatt into the grid. I'm not using that at that time of the day because I only have a fridge on. Nobody is home. But I'm pumping this energy into the grid. And this energy, maybe it's not required because we can't have it. So the future power system will deal with variability. You can see previously the generators had a very fixed output. So you could send them to a fixed point. But with the new type of generators, variability is going to be an issue that we need to deal with. This is the output of 3 big wind farms in Western Australia. You can see they can be anywhere. So this variability needs to be addressed. For the system operator to manage this variability, that will be a very, very difficult task. So what are the challenges? We need to balance load with generation at any second of any minute, any hour of any day, 365 days a year. And with that variability that I showed you, how difficult it is. So we end up with less inertia in the system. We end up with reduced ability to manage frequency. And the system strength is going to be lower because the new generation are fundamentally different from synchronous generators. And then we need to have dynamic voltage and reactive power capability. What will happen if we don't? What will happen if this balance is not managed? There will be a blackout. We have had so many blackouts just recently in the UK, in Argentina, even in Indonesia just recently. Yes? So we should learn how to avoid them. And we had one in South Australia, of course. Yeah? The whole estate went black. But we can learn from it, right? Because this is the future. This is the future of power system. We are not going back to coal. We are not going back to nuclear. Or maybe, I don't know. There are talk about new nuclears. But I know Japan is not very keen on nuclears. And Germany is phasing out. No more nuclear for Germany. And I think they're right. So what is future? It's really hard to predict. Somebody said future isn't going to be what it used to be. Normally we look in the past and then we project to the future. That's what we always did. But no more, because past is not going to be a good indication for future anymore. So we have to forecast. We have to be able to forecast as much as possible and as accurate as possible. Not only load, we need to forecast for solar, we need to forecast for wind. I don't know if this animation can work, but this is a Japanese satellite, a Himawari satellite that we use in our control center to ensure we can forecast at least the weather conditions accurately, and we can see what is coming. So you can see through the satellites how the cloud is going to come over, what is the wind movement, and how we can prepare for it. These are the graphs of what PV is doing, what wind is doing, what system load is doing. And in many cases, you can see the wind and solar is going up, where system load is going down. So they go in opposite direction a lot of time. So if you want to keep that balance all the time, you need to be on top of your game. This is what frequency is doing when these sort of things happen. So frequency used to be very constant. No, at some situation we end up with frequency just diving or frequency just rising. So we need to be able to manage those situations. So what are the trends? Of course, decarbonization. This is what all the governments around the world want to do. A commitment, an international commitment to decarbonize the system. That's what we all said we would do in Paris Agreement, didn't we? And then decentralization as a result. So previously we had a few generators that we knew where they were, we knew how much they could deliver, they were dispatchable. Now we have thousands of generators. We don't know where they are, we don't know how much they're going to generate, and we don't know how much load is requires. But still we have to manage frequency. Still we have to do our job. So decentralization is the key to this conference and how we can manage the process of decentralization of energy mix. Sector coupling, I think one of the speakers this morning said, you know, it's not only electricity. No, the heating, transportation, even water treatment, water desalination, there is so much interdependencies between different types of industry that we need to be mindful of. And then digitization or digitalization. So this is how we get the data into some meaningful and insightful business knowledge that then we can use to manage the system. This is where big energy data comes into picture. Because we create so much data that we need to do something with it. Sensors. We have sensors everywhere. If you have one of these in your pocket, it's likely that it has more than 10 sensors. And these sensors continuously gather data and continuously send this data to the internet. And the manufacturer knows what you are doing with your phone because of these sensors, because they gather this data and turn them into information and business insight. We have sensors in the power system, and these sensors gather information. We have smart meters now. A lot of old meters are replaced with smart meters. We have phasor measurement units in different parts of power system that continuously send information. We have a SCADA that every 4 seconds send thousands of information, and these information are gathered. And then we have Internet of Things, or Energy Internet of Things, which really is a means of managing the energy system, the transactive energy future that we are dealing with. And we have artificial intelligence, machine learning, and deep learning. So machine learning is what machine can do with structured data. But in many cases, we don't have a structured data to feed into machines. We have different data in different layers and not as structured. And these data are in the form of artificial neural networks that gets fed into a machine, and the machine has to make sense of it. So what is the purpose of what we are doing? So we need to be able to understand the dynamics of power system, be able to forecast what the load is, and get it from the weather data, weather information. We need to get all the information from these multiple users, thousands, millions of them. And then we mix it with, okay, what the country is doing, what the GDP is, how the growth is structured, what the price from energy market. And then we can turn this into time series analysis, turn this into clustering, because this amount of information, this amount of data is so hard to deal with. So we get clusters of these data such that we can understand the dynamics of different things. And then we get into deep learning. We get into deep learning from the power system, because this information, for example, the information of interrelation between voltage and reactive power, how it works with tap changing of transformers, how the machine can learn what sort of actions can be done. And then from this deep learning, we can extract features. We can say, oh, this interrelationship between these values paints this picture, that we need to do this. So this gives us insight that not only we can understand the interrelationship between different things, but also we can predict things. Not only descriptive analysis, but predictive analysis. And the future of this is that then we can say, oh, we can shape the future by doing this or doing this. And then we get into prescriptive analysis that shapes how the future of energy can progress. And the whole objective of this is to enable more renewables into power system, because the power system is changing and the characteristics of these generators are so different. We can't just let them come in and change the whole scenery without us being able to manage this. So we learn how to deal with them such that we can enable their integration. Big data can help us not only have relationship in vertical, house to utility, but horizontal, house to house, peer to peer. And then we can create platforms that can enable this interaction. technical challenges are not difficult. If you know this is Hadron Collider, and if you want to see the scale of this, this is a man here. That is the scale of this. So human beings can deal with technical difficulties. But it's not only technical difficulties. There is so much more interplay in the energy landscape. You know, there is regulation, there are markets, there are politician, policy. I'm sure all politicians want to interfere with energy landscape because that is what they have done. But smart grid can help. You know, we can create flexibility into power system. With data science, we can gather insight and information, and we can do a lot more things that we couldn't do in the past. So the past, the grid looked like this, very simple. Generators, transmission, distribution, and load. But now it looks like this. What can help this is a smart grid, because a smart grid, what it does, it brings a lot more, not only power flow. The difference is between a normal phone and a smartphone. A normal phone could only make phone calls. A smartphone can be a lot of things. I think you can only not brush your teeth with it, yeah? But there will be an app, I'm sure, in the future. So a smart grid can bring another layer on top of the power flow. You can have information flow, and you can see how everything's fit together. What future holds? Energy sharing. Our first speaker put up the ride-sharing scheme, which is a Grab or Uber. Future of power system will be energy sharing. So I will share energy with you when I'm not home and I'm not using my power. I can sell this energy to you at a cheaper price than what you can get from the utility. So platforms will be able to enable peer-to-peer trading between different players in the market. There will be innovative electricity market. These markets will not look like what the markets that we have now, that only clear between price and quantity. The future markets will have multiple time, will have multiple quantity, will have multiple price, and will have multiple reliability. Because I may not need 100% reliability. I may have appliances that they don't require 100% reliability. For example, if I have a pool in my house that has a pool pump, the pool pump can run any time. It doesn't need to run in certain times. Or if I have a water heater, if the water heater doesn't get electricity this hour, but can wait until next hour when the electricity is in abundance, then that can be another sort of reliability that I can allow. So the future market will be able to enable all of these. And then it can actually optimize network capacity. Currently, because things happen outside our control, network capacity is minimized. So the utility has to invest in the grid to put more lines with more cables. But if you orchestrate the load to match the generation, then the network capacity will be optimized. So this is what I called load flexibility. We have done a lot of optimization on the generation side, but we have done very little on the load side. So the load needs to be optimized. The load needs to be broken into what actually this load needs, what it does, what is the purpose. So the future will enable such a thing. And then we will have electrification. So we need to clean up electricity production, we need to decarbonize the industry, and then we need to turn everything electric. Transportation, heating, cooling, everything can be clean again. So what are the learnings for Indonesia? You are starting to have a lot of non-synchronous generation. I read in your Ministry of Energy report that by 2025, you will have 26% of renewables in your energy mix. So you need to have a very strong grid code. You need to ensure that the standards are met. So the distributed energy resource standards, you need to apply the latest standard. IEEE 1547 is the latest standard that applies to all inverters. You need to mandate that standard. And you need to ensure that there is enough essential system services like frequency support, load following, load rejection. There are so much that previously was given because we used only synchronous generators. Inertia, system strength. So these are the new essential system services that we need to have. And if we let, the growth of renewables only like a natural growth, you may run out of these services. So you need to have a strong program of implementing renewables in a very structured way. And then, of course, the balance between environment, reliability, and efficiency, the cost. You have to have a very balanced approach to these objectives. You can't have one without the other. So it is like a tricycle that, you need to have this tripod needs to have 3 pillars to stay balanced. So change is inevitable, and future is going to be much different from the past.
Sorry.
And this is the message for our industry.
Sorry, you have 2 minutes left.
Yeah, okay. These are my 2 last slides. I want to show you this. This is New York, 5th of May. This is Easter Parade, 5th Avenue. And you can see all carts, all horses, carts driven by horses. Maybe you can see one car here. Yeah? Only one car. All horses. This is 1913, same day, same avenue in New York. All cars. Can you spot the horse? It was really hard. So if you think that this is a change that is unprecedented, think again. Because the change is always here. Thank you so much.
Okay, thank you very much. That was a very insightful information given by Mr. Dean Sarafi. And now let's go into the last plenary speakers, and it's going to be Mr. Noriyuki Ono. He is Senior Manager, Technical Strategy Sections, and then Solutions System Department, Solutions Business Strategy Divisions, Mitsubishi Electric Corporation's Factory Automation System Group, Japan. So please welcome. Let's give a very big applause to Mr. Noriyuki Ono. All right, just want to remind you something. After this, we're going to invite all the panel speakers, and we're going to come with the question and answer session. So before we're going to have lunch, yeah. So perhaps there will be around 50 to 30 minutes for the question and answers while we are waiting for Mr. Uno to prepare his presentations.
Okay, hello everybody. My name is Noriyuki Ono. Today, I will spend about 30 minutes to introduce Mitsubishi Electric IoT solution. We call it eFactory. So these items are included to today's my presentation. Environmental changes in manufacturing. The expanding of IT, IoT, and the information infrastructure. First of all, let me talk about the background information of our e-factory. As we know that manufacturing has changed, products use it to be more standardized, and supply chains are fairly stable. Efficiency and quality were enough to solve customers' needs. But today's global economy is more complex and customers' needs become much more diverse and sophisticated than past. At the same time, technology advancements also made various things possible. So recently, there emerged a number of cost-effective and flexible data collection, storage, and processing solutions, such as IoT and cloud or edge computing. And first, data collection technology. With the development of data collection technology, a huge amount of data could be obtained from the production site in high speed by using high precision sensor. And the second one, data communication technology. The development of data communication technology has made high speed and real-time communication of large value data, including image data possible. And the third one is processing technology, with the utilization of cloud computing and edge computing, data acquisition, transmission, and data security is developed. Edge computing is essentially the process of decentralizing computer services and moving them close to the source data. This can have a significant impact on latency, as it can drastically reduce the value of data moved and distance is traversed, which makes a real-time feedback possible. And the last one is data analysis technology. With the development of data analysis technology, high precision analysis is possible. Advances in algorithm and AI enable us to simulate complicated manufacturing situation and find actionable signal in data that was previously too large or complex to track. World initiatives toward IoTization, towards the manufacturing evolution, various movements has come into view around the world. The term Industry 4.0 was revived in 2011, and the Industrial Internet Consortium in America is founded in 2014. Japan has also proposed it, connected industries, as a new concept framework in which industries will create new added value and solution to various problems through the application of modern information technologies. Oh, don't forget, Making Indonesia 4.0 is founded last year. And what is e-factory? So recently, IoT trend is booming rapidly. Before this IoT boom, Mitsubishi Electric already announced the concept of e-factory, which utilizes FA and IT technology for improvement performance of any manufacturing enterprise. Mitsubishi Electric announced the concept of e-factory in 2003, which is much earlier than the announcement of Industry 4.0 of foundation of IIC. E-factory is an integrated solution which utilizes FA and IT technologies for improve the performance of any industrial enterprise. With this model, I will tell you more about it. This model is roughly divided into 3 layers, including shop floor, IT system site, and edge computing site. Edge computing site is an area where various processes, such as collection, diagnosis, and result, feedback, and performed. With the utilization of edge computing layer, there are 3 major improvements could be brought to your production site. First one is data visualization. Data generated from the shop floor could be collected in real time and visualized in graph. Second one is real-time data analysis. With the primary processing technology, or what we call edge computing, data can be transformed into meaningful information, makes it much easier for further analysis. And with this feature, only required data is sent to IT system, which reduces the load for both network and service. Third one is real-time result feedback. Analysis result could be feedback to the shop floor layer from both IT system and edge computing layer. In addition, e-factory solutions are not only for the newly added equipment. Thousands of e-factory systems has been installed additionally onto customers' existing equipment. And the core technologies and products to realize e-factory. To realize e-factory, mainly 3 core technologies are required. First, industrial network technology. Industrial communication networks are the backbone of e-factory solution. In order to satisfy different requirements, properties such as large capacity, high speed, and high reliability are required. And for the FA, IT mixed communication, an open standard protocol is also necessary. The answer to this demand is the CC-Link IETSN, so protocol, which isn't only a protocol, but also a solution of optimize the entire system. Next, FA, IT, linkage technology. This technology enables information linkage between controllers or device with IT system. Mitsubishi Electric offers different kinds of products, such as MES, interface module, and GOT, graphical operation terminal, helping our customers realize FA, IT linkage on their own production site. And finally, control technology. This isn't only about robot technology for automation. Sensor control technology for data collection is also included. E-Factory Alliance. So, FA technology or a product is just one component of the best possible complete solution. When adding components, it's useful to include the enterprises of companies who are leading the market as a partner program for the realizing best e-factory solution. We have created an alliance which partner who agree and approve of e-factory concept, including software partner, SI, system integrator partner, and device partner. And there are already about 700 companies joined in our alliance as a partner, and we will achieve new business creation together. From now, I will introduce e-factory implementation examples at Nagoya Works in Japan at Mitsubishi Electronics. E-factory production innovation initiatives. In Nagoya Works, production methods are varied as the products we produce. For example, laser cutting machines, production value is about 15 units a month, and the assembly processes are complex. In this case, an assembly support system is needed to help workers finish their jobs efficiently without human errors. And the products like a PLC, program logic controller, or electromagnetic switch, their production value is about 500,000 units a month. So we want to continue improve productivity and reduce quality loss. In this situation, a management system for entire production line is necessary. As you can see, e-factory solution is designed differently depending on different requirements. IoT maturity level and the management scope. When we plan improvement activities, we usually use a certain index, which we called SMKL, referred to a smart manufacturing Kaizen level. The horizontal line shows management range, and the vertical line shows maturity level. With this index, it's easy to mark how much level we have achieved and discuss where to the next stage. Usually, the target activities which are positioned left down requires less investment, and activities which are positioned right up require large investment. Assembly work navigation system. Now let me introduce our first solution, the screw tightening job navigation system in our PLC plant. Work cell production method was implemented about 10 years ago because it's suitable for the various projects manufacturing in small lot. To reduce human mistakes, we introduced the work navigation system, which is built by combining our PLC and the GOT indicator. So this picture shows you the navigation system for screw tightening job. Human mistakes are prevented by giving electronic instruction or work procedures, and LED lamp lights up to indicate the next driver of a screw to be used. And by using the sensor installed in back of the driver, screw tightening can be checked automatically. Data like product quality and workers Work time is collected and sent to IT system in real time, and all the data is stored in our eFactory database. By analyzing data collected from work cell, Kaizen point, improvement point are visible through the dashboard screen. For example, the graph of assembled quantity of each worker shows us which worker need to be trained more. Through the analysis of the performance data, we could also improve product design and production produce. With this system, man-hour required for training newly assigned workers have been reduced to 1/3, and the products whose loads are almost zero. Now, I'd like to show you a short video.
Where is the speaker?
10 years ago,
You know,
the past 10
where is the
years, the
speaker?
number of mistakes has
Like
been reduced to 1/10.
Enggak.
The e-factory technology is fully mobilized to achieve zero
Maybe you can
mistakes and renovate the sequencer assembly cell
explain
on the
what the
fifth.
video is
Collaboration
about.
between workers and machines has been ensured.
So we have still this.
This assembly cell features a job instruction system,
How
which was
about we
built
use
by
this
combining
device?
our sequencers and indicators.
Dan harus di ini kan coba nanti dulu. You can use this one.
Now,
Maybe
let's take
the
a look at
converter
the
audio.
screw tightening job instruction system.
Install benar enggak apa?
There are two
Install dulu.
key points in the work: using the correct parts and installing the parts according to the correct method.
Iya, bisa kena. Gitu ya. Minimal satu ini. Nanti langsung ke ini. Udah, coba. Ting ting mau enggak, Pak? Oke. Play. What?
Various types of sequencers and indicators are assembled on the 5th floor, and different work procedures and parts are used. For this reason, the cell production method was employed more than 10 years ago. The cell production method is suited to manufacturing various products in small lots. Mistakes occur because a single worker performs the entire work. In addition to skilled workers, quite a few inexperienced workers, including newly assigned ones, work at the production sites. To reduce mistakes, Nagoya Works started to work on improvement more than 10 years ago. Over the past 10 years, the number of mistakes has been reduced to 1/10. The e-factory technologies were fully mobilized to achieve zero mistakes and renovate the sequencer assembly cell on the 5th floor. Collaboration between workers and machines has been ensured. This assembly cell features a job instruction system, which was built by combining our sequencers and indicators. Now, let's take a look at the screw tightening job instruction system. There are two key points in the work. using the correct parts and installing the parts according to the correct method. In the screw tightening job instruction system, the indicator screen in front of the worker displays the type and number of screws and the type of electric screwdriver to be used. The LED lamp lights up to indicate the next screwdriver to be used. The worker can accurately take out screws and select the next screwdriver without checking the job instruction. The indicator displays the screw tightening position and tightening order. The color of the tightened screws changes on the display so that the next screw tightening position can be checked at a glance. In addition to instructing the work procedures, the system can automatically determine the quality of screw tightening by using the sensor installed in the back of the screwdriver. If a screw is not properly tightened, the red patrol light and buzzer informs the worker of a problem, and the screwdriver is turned off to prevent the worker from performing the next job. All the data of screw tightening torque and time is collected by sensors. The data is linked with the products, workers, and dates and times of work, and is stored in a database on a real-time basis to ensure traceability management. This instruction system has made it possible to standardize the work and eliminate dependence on the experience and senses of skilled workers. This cell production enables newly assigned workers to ensure high quality in their work. The work improvement is facilitated by analyzing the huge amount of data derived from the instruction system. For example, the work time of each worker can be identified based on the graph of the average work time. Intensive training can be offered to workers who take a long time to complete their work. The number of improperly tightened screws can be displayed for each worker. Effective training can be offered to workers who often cause screw tightening defects. The quantitative data is automatically collected, and the effect of the training can be checked at a glance. The graph showing the number of defects by work process helps identify the processes in which screw tightening defects often occur. Improvements can be made quickly by jig replacement and design change. The instruction system has helped standardize the assembly work. The man-hours required for training newly assigned workers have been reduced to 1/3 through pinpoint improvement activities. The familiarization period has been halved, resulting in a significant increase in productivity.
Okay, I'd like to introduce another implementation examples at my company. So, production with a robotic assembly cell. This is an implementation example of Nagoya Works Kani factory. So, Kani factory, that is a plant name. So, produce electromagnetic products with a small lot and multi-cycle production is required. Kani factory has added a robotic assembly cell which utilizes Mitsubishi Electric industrial robot made for and uses QR code to manage production information. So now I'd like to show you a short video about 3 minutes.
E-Factory. Until now, the production line was almost 35 meters long. From contact insertion to assembly, and even tightening screws, the robot cell compactly consolidates 6 processes. Compared to line production, there is a significant improvement in productivity. Optimal productivity was realized in robot cell with human and small-scale facilities. The robot cell utilizes e-factory in an effort to further improve quality and productivity. First, there's traceability. For example, production information such as parts and lots ordered by customers are all managed using QR codes. Production follows the instructions of one QR code for each block of 6 processes, ensuring error-free, expedited production management. After shipment, the information can be used as delivery information and for quality assurance. Robot hands assess quality through fine measurements performed during assembly and collect real-time data for all parts. This helps improve assembly quality. For the delicate process of screw tightening, a vision system collects and assesses visual data to improve assembly quality. Collected data is analyzed for optimal control to improve productivity. Through coordination with e-factory alliance partner devices such as code readers and a vision system, optimal control is realized in all processes. We break down and analyze the collected data to provide feedback to the production site to further improve quality and productivity. E-Factory utilizes collected know-how to envision the future of monozukuri, the art of making things. We will widen our scope, improve performance, and move forward with our partners.
Okay, let's move to the next edge computing
Sorry,
platform.
excuse me, you have 5 minutes left. Only 5 minutes left.
Oh, really? Okay. And now, I'd like to move on to the another part of the presentation, edge computing platform, edge cross. As I mentioned before, edge computing is the key technology for smart manufacturing. With this technology, we could solve many issues at production site. Edge cross and e-factory solution. Edge computing is the key technology for optimizing the entire e-factory solution, and the edge cross platform will facilitate the utilization of e-factory solution. In our opinion, IT system layer and the FA layer are convention field for each companies. But in the edge computing layer, besides the competition, we could collaborate together to create new added value. The surrounding environment of monozukuri manufacturing, we already know that edge computing is data process technology at network edge close to the production site. It has a lot of benefit, like lower latency, real-time response, and high-speed data process. Putting all the analysis on IT system use it to be an efficiency way for data processing in manufacturing. However, with the advancement of data collection technology, a large quantity of data may be generated from the production site, which is too heavy for the network and the service. So, utilization of edge computing is becoming more and more important. Okay, I will skip some page. association structure and activities of H-Cross Consortium. So, platform H-Cross is built by H-Cross Consortium. Here is the association structure of consortium established in 2017. Consortium's main object is promotion of H-Cross. And Mitsubishi Electronics is one of the 8 board governors, even though our big competitor, Omron, is here. At this point, we collaborate together to promote the H-Cross platform. And Mitsubishi Electric also provides software and production suitable for H-Cross platform, including H application, industrial computer, and data collector. Now let me introduce one of our H application products, real-time data analyzer. Okay, I will show you the video. So use it, our edge computing software, real-time data analyzer at Nagoya Works in Japan.
We would like to introduce a case study on cost reduction using the Edge Cross-enabled software Real-Time Data Analyzer. In the assembly process of the stator for our small capacity servo motors, thermosetting resin is molded at the end. When molded resin has poor appearance, even if the preceding processes have been successfully done, products end up being disposed. This results in loss of material cost and time. To solve this problem, production lines used to be suspended when frequent molding defects or any visible abnormalities were identified by operators. Measures against molding defects have been taken by maintaining resin molding machines. However, believing that there is room for reduction of loss, we have explored further improvement. As one approach, we have considered how to identify signs before an increase in molding defects is recognized by operators to carry out appropriate maintenance. We have decided to add our Edge Cross-compatible industrial PC, MEL IPC, without modifying the existing resin molding machine. Using Edge Cross, only the data of molding process is acquired. Data related to molding defects can be extracted using the data analysis software Real-Time Data Analyzer. Based on the extracted data, we created diagnostic rules to identify increasing trends of molding defects. It turned out that an increase of molding defects can be predicted by monitoring data from a resin molding machine with the diagnostic rules. Now we found the way of reducing the losses of material cost and man-hours by performing maintenance when signs of an increase in molding defects are identified and implementing the PDCA cycle. We will reduce molding defects drastically by expanding data collection and developing analysis methods. We will continue to make on-site driven improvements, such as improving resin molding machines and molding methods.
Okay.
Sorry, I think that you ran out of time, so we can go to the
Okay,
Q&A
I see.
sessions or SMS questions. Thank you.
All right, so I gave various explanations. So while Mitsubishi Electronics is at the cutting edge, It's also trial and error every day. Solve so customer or your problems together with you. As a result, Mitsubishi Electric want to grow with its customers. So thank you for your attention. That's all.
Thank you very much. So I think I'm going to invite all the keynote speakers to come forward and take your seat here. And we're going to come with the last sessions of the presentations, that is question and answers. But how much time do we have now? 15 minutes, is that right? The committee, please. Is it 50 minutes?